Last time we talked about the determinant function, and today I want to talk about some of its properties. So first of all, if we have an upper triangular or lower triangular matrix, it's very easy to take the determinant. If A with entries ij, aij, is upper or lower triangular, then the determinant is just a product of the entries that are on the diagonal. The reason is that A is going to look like, let's say it's upper triangular, so it's got entries on the diagonal, anything at all above that, and then all zeros below the diagonal. And determinant is a sum of plus or minus products of entries, one per row, one per column. So positive or negative that, a sum of these. Now in this case, the only way to choose a product of entries, one per row, one per column, is to choose the diagonal ones. So the only way to do this for an upper triangular matrix is to take the diagonal entries. Then the corresponding permutation is 1, 2, 3, etc. up to n, which has no inversions. So when we figure out this sign, which is -1 to the number of inversions, that has 0 inversions. So the sign is -1 to the 0th, which is 1. So we get a positive sign here. So we don't need a minus. Alright, another fact that makes it easy for us to take determinants sometimes is if any row is all 0, then the determinant is 0. And the reason is, again, determinant is a sum of plus or minus products of entries, one per row, one per column. Well, if we have to take something in every row, then we're going to have to take something in that row that's all 0. And then we multiply it by the entries in the other rows. Well, it's 0 times something, so it's 0. So the 0 row contributes a 0 to each product. So that means the sum is 0. A sum of a bunch of zeros, whether they have plus signs or minus signs, has got to be 0. I'm sorry, this should be a 2 because I'm giving you property number 2. I'm numbering the properties a little bit different than they're in the book. I'm numbering them in a way that I think makes more sense. So now let's look at property 3. If we have a matrix that has exactly 1, 1 per row and 1, 1 per column, then the determinant's going to be plus or minus 1. Let's look at a special case. Let's look at a matrix that's got 1s on the diagonal, and then a 0, and then ones, and then a 0, and then ones. So there's two places on the diagonal where there's a 0 instead of a 1. Then let's put a 1 right here and a 1 right there. So we took those two 1s off the diagonal and put them here. Let's say this is row I, and this is row J here. So no matter what I and J are, this determinant is -1. And the reason is, similar reason, the determinant is a sum of products of entries, 1 per row, 1 per column, with a plus or minus sign. So we can see that the product of the non-zero entries is going to be 1, because we've got 1 times 1 times 1 times 1 times only 1s for the terms of the determinant that are not 0. So the only question is, does the permutation corresponding to this arrangement of 1s have an even number of inversions or an odd number of inversions? Now the permutation corresponding to this arrangement of 1s is 1, 2, 3, etc. up to I minus 1, and then J instead of I, and then I plus 1 up to J minus 1, and then instead of J, I, and then J plus 1 to N. Alright, how many inversions does this have? Or at the very least, can we see if the number of inversions is even or odd? Inversions are, well, there were no inversions until we swapped this I and this J. So now that we swapped them, J is a bigger number than all of these. So Ji plus 1 makes an inversion, Ji plus 2, etc. up to J minus 1. And then Ji is an inversion also. Now 1, which used to be here, is smaller than all of these numbers that passed. So that means that I plus 1i is an inversion, I plus 2i, etc. all the way up to J minus 1i. So we have J minus 1 minus I inversions here, and then J minus 1 minus I inversions here. And then 1 inversion for the I and J that got swapped. Well, 2 times anything plus 1 is an odd number. That's odd. So that means that we're going to get a sign of -1 to an odd number, which is -1. Property 3. All right, property 4 is very easy to state, but a little bit harder to see. So I think I'm just going to state it and say, don't worry about the proof. You can read in the book if you like. Property 4 is that for A and B square, we only take determinants of square matrices. Determinant of AB equals determinant of A times determinant of B. which I guess is the easiest possible formula it could be, seeing that we're multiplying A and B here. The easiest formula would be determinant of A times determinant of B, and it happens to be true. And let me just write down here so you remember the reason is not so easy to see, because multiplying two matrices gives a new matrix with sort of complicated entries. Five, the determinant of A transpose is just the same as the determinant of A. You can show that when you flip a matrix this way, a permutation which had an odd number of inversions ends up being another permutation that has an odd number of inversions. Similarly, if it had even number of inversions, you flip the matrix and then you get another one with even number of inversions. So transposing the matrix doesn't do anything at all to the determinant. So that means we said that if a matrix has a row of all zeros, the determinant is 0. Now if we transpose the matrix and doesn't change the determinant, we can say a matrix with a column of zeros has determinant 0. So anything that we can say about rows, we can say about columns. That is, the effect that rows have on the determinant is the same that the effect that columns have on the determinant. Alright, now one thing we've been spending a lot of time on in this course is row operations. So it's natural to ask, what do row operations do to the determinant? So we've got 3 row operations. First of all, swapping rows multiplies the determinant by -1. The reason is that A becomes PA, where P is the matrix that I drew before that looks almost like the identity, except it has 2 1s in the wrong place. So P looks like the identity. Maybe I'll draw it again rather than saying it in words. P looks like this matrix that we just said has determinant -1. So that means the determinant of PA, because doing a row operation on A is multiplying by, this is the matrix that swaps rows I and J. This is determinant of P times determinant of A, which is negative determinant of A. So swapping rows multiplies the determinant by -1. How about if we multiply a row by a constant? Now that multiplies the determinant by the most obvious thing, by this constant C. And the reason is that this is left matrix multiplication by the matrix that looks like the identity except it has a C in one place. Has zeros everywhere else. So the new matrix is, let's say this is P, The new matrix is PA with determinant equal to determinant of P times determinant of A. The determinant of this matrix, which is diagonal, since it's diagonal, it's upper triangular and simultaneously lower triangular. So the determinant is just the product of the diagonal entries. So that's C times determinant A. So far row operations either multiply the determinant by -1 or by some constant C, whatever we're multiplying a row by. Now we've got that last row operation where we add a multiple of one row to another row. So adding C times row I to row J keeps the determinant exactly the same. And the reason is that A becomes PA, where, well, let's write out the matrix that adds C times row I to row J. It's going to have all ones on the diagonal. And then let's say here's row I and here's column J. So we'll have a 1 here, every one on the diagonal, and then a C off of the diagonal. I'll put the 1 here. So this says that row I becomes row I plus C times column J. Oops. I wanted row J to become row J plus C times column I. So C times row I. So let me change the I and J here. It says row J becomes row J plus C times row I. Well, this is an upper triangular matrix and its determinant is just 1. So that means that the new matrix is PA and has determinant of PA equal to determinant of P, determinant of A, which equals 1 times determinant of A. So the determinant doesn't change at all. All right, now some consequences of these row operation determinant properties are that if we multiply A by a constant C, so that's every single entry in the matrix, not just a single row, then the determinant of that result is C to the n times A, assuming A is n by n. Well, that's because multiplying any row by C changes the determinant by a factor of C. And then if we do that to n rows, we're multiplying the determinant by C and C and C n times. And so we get C to the n times A. So that's one consequence. Another consequence is if two rows or columns, well, if two rows are equal, or if two columns are equal, then the determinant of the matrix is 0. And one way to see this is that suppose we swap the two rows. So swapping two rows multiplies determinant by -1, we said. But swapping two equal rows doesn't do anything to the matrix. So if we look at these two facts simultaneously, we have determinant A has to equal negative determinant A, because we're changing the determinant by -1 and simultaneously leaving it alone. But the only number which is equal to its opposite is 0. So that means that determinant has to be 0. Now another consequence, which is very similar, is that if one row is a multiple of another row, then the determinant is 0. So they don't have to be exactly equal. If one is a multiple of another, we know the determinant is 0. Let's say if row j is a multiple of row I, then the determinant is 0. Let's say if row j is c times row I, so that we have a name for this multiple. So let's start with A. And let's let PA be A with row j multiplied by 1 over c. I'm thinking of c as a non-zero number. Of course, if one row is 0 times another row, then we have a row of zeros, and we know the determinant is 0. So let's put PA be the matrix A with row j multiplied by 1 over c. So P does the operation, the row operation of dividing a row by c. So if j was c times row I, then when we divide row j by c, then we've got two rows are equal. So then the determinant of PA equals 0, because it has two equal rows. But the determinant of PA is determinant of P times determinant of A. Now the determinant of P is 1 over C. If the determinant of PA is 0 and the determinant of P is 1 over C, then we've got 0 equals 1 over C times something. So that something must be 0. Another consequence is that we know the determinant of the inverse of a matrix if we can invert the matrix. So if A is invertible, then the determinant of its inverse is 1 over the determinant of A. And the reason is that A times A inverse is the identity matrix. So that means that determinant of A inverse is determinant of the identity matrix, which is the diagonal matrix with all ones. So that's 1. But the determinant of the product is the product of the determinants. So this is determinant of A times determinant of A inverse. So we're saying determinant of A times something equals 1. Well, I guess that means that determinant of something equals 1 over determinant of A. And if A is invertible, we know its determinant is not 0, so we can divide by A here. All right, now I'm going to say a little bit about solutions of equations. So let's let A be a square matrix. Then the equation AX equals 0, which is called a homogeneous equation. Homogeneous because the right-hand side is equals 0. This always has a solution x equals 0. If A is invertible, it's the only solution. And that's because AX equals B implies that X equals A inverse B. So we can multiply both sides by A inverse and find that X equals A inverse B. B here is 0. So AX equals 0 implies that X equals A inverse 0, 0 vector. But when you multiply any matrix by the 0 vector, you just get the 0 vector. So there's the one solution if A is invertible. Now, if A is not invertible, then we have the solution x equals 0 still, but we have infinitely many more. Then there are infinitely many more solutions in addition to x equals 0. So let me just do an example of that. Let's look at 1, 2, 3, 4, 5, 6, 2, 4, 6, x equals 0, 0, 0. Now this matrix has got determinant 0 because we can see that the third row is a multiple of the first row. So let's do row operations to solve this. So we've got, I'll take away 2 times row 1 from row 3, just get rid of that row 3 because we can see that already. Well, already here. So row 3 becomes row 3 minus 2 times row 1, and row 2 becomes row 2 minus 4 times row 1 to get rid of the 4 here. And that gives us 1, 2, 3. Well, there should be zeros in here because the right-hand side is 0. 0. 4 minus 4 is 0. 5 minus 8 is negative 3. 6 minus 12 is negative 6. And then 0, 0, 0. And then row 2 becomes negative 1/3 of row 2. To give us 1, 2, 3, 0, 0, 1, 2, 0, 0, 0, 0, 0. Now if we solve that, each column corresponds to a variable. The third column doesn't have a leading 1 in it, so we let that third variable just be some dummy variable t. Then the second equation says that x2 plus 2x3, which is t, equals